Okay, I want to look at something called apparent weight here. And this is something that because the Earth is spinning on its axis, you don't weigh quite as much as you would if it wasn't spinning on its axis. And something that we need to consider is that someone who's, for instance, on the equator is traveling around a circle. It's about this big. They do it in a 24-hour period, so they're going to have a certain velocity around this thing. In fact, if you're on the equator, you're going at a little bit more than 1,000 miles an hour, which is a pretty good clip. Centripetal acceleration is v squared over r, and r is fairly big, and so the v squared ends up, even though it's a pretty large number, v squared over r is not a terribly large number, but still it'll alter your weight somewhat. If you're up here at a latitude, maybe approximately where Moses Lake is, you're traveling around a smaller circle in that same period of time, and so you'll have a different centripetal acceleration. Also, something important, the centripetal acceleration is always in the direction of the center of the circular path you're traveling. For someone who's up at the latitude of Moses Lake, the center of that path is about here. It's not at the center of the Earth. It's only at the center of the Earth for people on the equator. So that's something that'll happen. For someone who's at a very high latitude, they're traveling in a very small circle. It's the Earth's axis that you would measure the distance to. And for someone who's at the North Pole, they're not traveling in a circle at all. They have no centripetal acceleration, which means they don't have a difference between their true weight and their apparent weight. The true weight is the gravitational force equation that we looked at, the capital G times the mass of the Earth times the mass of them divided by the radius of the Earth squared. And that'll be a force that's acting on everyone, but it's not necessarily what a scale will show you. So let's move on a little bit with this. And the first thing I want to do is figure out the, where did I put that calculation? Somewhere here. Oh, well, it'll turn up. Okay, the first thing I want to do is figure out the distance or the radius of the path that you're traveling on at different latitudes. Again, if this is the Earth, this could be the North Pole up here, South Pole up here, and we're just looking at it as like a disk right now. And this is the axis of the Earth's rotation. For someone on the equator, the radius of their path, that circular path that they're going to travel, is going to be the radius of the Earth. And if we figure out someone at a different latitude, we're not going to worry about southern hemisphere latitudes, but what's going to matter is the angle between a line from the center of the Earth to where you are on the Earth, for instance, right there. This is the angle that'll matter. And the mathematics will end up being the same for the southern hemisphere. It's the angle between this equator line here and whatever line is drawn to them. But the distance that they're actually, the radius of the path they're actually going to be traveling is this distance right here. Okay. Well, this is also going to be the radius of the Earth here. It's the distance from the surface to the center. This angle theta here will equal this angle up here, and we have a right triangle right here, or a right angle there, and this side here is the side adjacent to the angle. this is the hypotenuse of the right triangle, and adjacent over hypotenuse is the cosine of theta. This distance here is the radius of the Earth times the cosine of theta. Now, the cosine of 0 degrees down here at the equator is 1, and so this distance for somebody on the equator is just going to be the radius of the Earth. Up here, the cosine of theta is going to be 0 when you get up to a latitude of 90 degrees, and wouldn't be traveling in a circle at all in that case. Okay, now some more math that we need to figure out here. One thing that's going to happen is that the acceleration is v squared over r, but the v, the speed, is going to be, what I'm going to do instead of calculating v, I'll do that for one problem maybe, but it'll equal 2 times the radius, or 2 pi times the radius. That's the distance traveled in a circle around here, divided by how long it takes to do that. And we can write this as 2 pi, 1 over the period is the frequency. So we can write it like that. And this thing turns out to be the angular velocity in this case, which we've used the Greek letter omega to stand for that. And so we can say that v is equal to omega r. Well, if we use that, then the centripetal acceleration, I'll put a subscript of a c on, is going to be v squared omega squared r squared over r, and r squared over r is just r. So we can think of that as being r omega squared. And that's what I'm going to use for the most part to calculate the centripetal acceleration. And every point on Earth is going to have the same value of omega. So if we look at different latitudes, everybody's going to have the same value of omega, but they'll have a different radius for the path they're traveling. And in fact, the radius of the path they're traveling is what we figured out up here. So that centripetal acceleration will equal r sub e cos theta, the radius of the Earth, times the cosine of their latitude, times omega squared. So that's a way that we can figure it out. And once we figure out omega for the Earth, we won't have to recalculate radii or anything else. Oh, there it is. That's the thing I was looking for, hiding down there. Okay, anyway, Earth turns on its axis in about 23 hours and 56 minutes, which ends up being approximately 8.616 times 10 to the 4th seconds. So that'll be t. Omega is going to equal 2 pi radians divided by how long it takes to turn on its axis. And I've mentioned a few times now that the Earth turns on its axis in 23 hours, 56 minutes, and a few seconds. So if you plug that in here, you'll end up with a value for omega of about 7.293 times 10 to the minus 5th radians per second. And so that's something that's going to happen in this case. All right. Now, the reason we've been doing this stuff is because we're going to have centripetal acceleration. The forces that are acting on the object have to provide that centripetal acceleration. And the two forces, let's imagine that someone is on the Earth, and I'll draw a very crummy circle here, but that's okay. Here's the center of the Earth, there's the axis. And this person will not be to scale, but let's suppose somebody is standing on a bathroom scale here, And there they are, standing on the scale. The two forces that are acting on them are going to be their weight, and the weight is actually equal to G times capital M, the mass of the Earth, times the mass of them divided by the radius of the Earth squared. This is what we call the true weight of them. And the thing in parentheses here is what we think of as the acceleration due to gravity. So this is going to be m times little g. Now, usually when we use little g, we're using something that's actually corrected for the effect of this rotation. But here I'm going to think of this as the true value of the acceleration due to gravity, or it's the acceleration due to gravity you'd get if the Earth was not rotating. But that's what the weight is going to equal. And the direction of that weight is going to be down toward the center of the Earth. Okay. Now, it's not necessarily an arrow that reaches all the way to the center of the Earth, but it's close. Now, there's another force that's acting on them, and that force, the normal force, I'm going to think of it as mg star, excuse me, and g star is going to be the direction of the acceleration due to gravity where they happen to be, and it's also going to be corrected for the rotation of the Earth. And so we'll see what's going to happen when we get that. These two forces together, the weight plus the normal force, are what have to produce that centripetal acceleration. And so they'll be ma sub c, something like that. Well, the centripetal acceleration points from where the person is into the rotational axis of the Earth. So here is the ma sub c. It's going in that same direction. Well, I have to have w plus n is equal to that. That means it's going to have something coming in here, and then n is going to have to be a vector that points in this direction a little bit off from the direction of w, and the direction of n, the line of that, is actually the direction that we think of as down when we're standing at a point on the Earth. So this is all just a picture here. Now, something that I can do with this diagram, I can divide m out of every one of these terms and just draw the vector that or the things that I have with the accelerations. So I would have little g in this direction, g star up in this direction, and then that thing in that direction. And by the way, this angle here is the latitude angle, theta. So this ends up being kind of a complicated mess, but we'll live through it. Okay, I'll just draw a nice big diagram here, and or a bigger diagram. And what we'll have is that what we usually think of as G is going to point down in this direction. I'm going to have a centripetal acceleration that points in this direction, a sub c, and this isn't to scale. Turns out the centripetal acceleration is pretty small compared to g, but I will have the angle theta here. And then I'll have what I'm calling g star point up in this direction. And G star is what you would actually experience for the acceleration due to gravity at the point that you are on Earth. It's tweaked by the fact that you've got this centripetal acceleration in there. So if you drop a rock or something and time it to determine the acceleration due to gravity, it's G star that you would be getting the magnitude of. Well, here's the thing. We can calculate just plain G. That turns out to be G times the mass of the Earth divided by the radius of the Earth squared. Okay, so that's a number we can calculate. We know how to calculate the centripetal acceleration. The centripetal acceleration, I had a few pages back, that's that thing that's the radius of the Earth times the cosine of this angle here, the cosine of your latitude, times omega squared. And omega is the same for every point on the Earth, so we can calculate that. And from that, we can figure out what G star happens to be, except we have to use the law of cosines to do that. So let's see how it works out. And I'm also, just for the heck of it, I'm going to calculate this angle like phi. I just named it that. And that's the angle between the direction to the true center of the Earth and the direction that a rock would fall if you dropped it at whatever latitude you're at. And it turns out it doesn't fall exactly toward the center of the Earth, but you're never going to be able to tell the difference. So we're not going to worry about that. But anyway, I'll just go ahead and calculate it anyway. So here's what G star would equal. G star squared, and I'm going to use the law of cosines here. Law of cosines, you take one of the sides, operate it, square it, add it to the other side squared. So it'll be just plain G squared plus AC squared minus 2 times G times AC times the cosine, whoops, missed the cosine, times the cosine of the angle between AC and G, which is theta. Or G star will equal the square root of all that stuff. So G squared plus AC squared minus 2G AC cos theta. Okay, so we can figure out what the acceleration due to gravity will be based on these things that we know. By the way, all of these calculations I'm doing right here are assuming that the Earth is a perfect sphere, which it is not. However, we're just going to assume that for this little exercise. And if you want to figure this out for a bunch of different latitudes, you end up with a different value for AC at each latitude. So you have to figure that out. You have to plug in the R sub E cos theta, or figure out the radius you're traveling, and well, that's what you have to do when you figure out AC, and then plug in the different values of cosine of theta. And it's a monotonous and repetitious calculation, especially when you have to stick it into here. And there's nothing better than doing monotonous and repetitious calculations than a computer. So I did this in a spreadsheet. Things I put into the spreadsheet that I used again and again. The G, the gravitational constant, 6.67. And I actually looked these up and had about 4 sig figs on all of these, although I didn't show them all. But got the units over here, Newton meter squared per kilogram squared. And I didn't feel like monkeying with the formatting to get it all to show. Got the Earth's mass here. I have the radius here. This is the mean radius, and I'll show you something in a little bit that this isn't quite correct. But anyway, 6.37 times 10 to the 6 meters. And then the value of G you get if you take this capital G, multiply it by the Earth's mass, and divide it by this radius squared, and you get 9.8203 meters per second squared. Okay. And then here's the value of omega in radians per second, 7.29, and I did have more sig figs on than that, but I'm not showing them all. Anyway, we have that. So for various latitudes, and I just did every 5 degrees, except I tossed in 47.18 degrees, which is about the latitude of Big Bend Community College. So this is where we are. It's pretty close to it anyway. And then go on up to 90 degrees. Calculate the centripetal acceleration in meters per second squared. At the equator, it's 0.0339 meters per second squared. Now, acceleration due to gravity is 9.8203, and this points in the direction opposite the acceleration due to gravity for somebody on the Earth's equator, because don't have a picture drawn, but if somebody's on the equator, the gravitational force is in here like this. The centripetal acceleration is exactly in the same direction. There's no triangle to mess around with. And the normal force that has to support them is in this direction. So here's N, here's, I don't know what to call it. Anyway, the force of gravity, which is the capital G times the mass of the Earth times the mass of them. And actually, this would have to be the mass times the acceleration due to that. But the normal force ends up equaling this force minus the centripetal acceleration force, or the centripetal force. So exactly opposite for somebody on the equator. And what we get is 9.7, basically 9.79 meters per second squared at the equator. And there's no angle between the G star and the G at the equator. And so they're pointing in the same direction, so you don't have to do that. Then you can see it's not a big effect anywhere. 0.0339, that's 3.39 centimeters per second squared out of 980, whatever, 980 some. Let's see, 5 degrees, it's getting smaller. The centripetal acceleration decreases as you go up in latitude because the radius of the path you're traveling decreases. And remember, the centripetal acceleration is the radius of the Earth cosine theta times omega squared. Omega never changes, but this gets smaller as you go up in latitude. Cosine diminishes as you go from 0 to 90 degrees. And by the time you get to 90 degrees at the North Pole, there is no centripetal acceleration. So there's no difference between the regular acceleration due to gravity and what we get for this calculation. So let's do I've got a couple of example problems with this, and they're not super hard or anything, but go ahead and look at those. And we'll refer to this diagram because otherwise you'd have to go through a kind of brute force calculation for every one of these. I forgot to blow up the font size on this. But you've got a handout you can print off. It's asking, says the acceleration due to gravity at, whoops, that's the wrong problem. That's the second problem. Says if the Earth were a perfect sphere of radius 6.37 times 10 to the 6 meters, what is the percent difference between your true weight and your apparent weight at the Earth's equator? Well, your true weight is the G times the mass of the Earth times the mass of you divided by the radius of the Earth squared. Okay. Your apparent weight, and by the way, this stuff here is what I call just plain G. Apparent weight, so you could write this as the mass of U times the acceleration due to gravity if the Earth wasn't spinning. Apparent weight is going to be the mass of U times G star, that thing that we calculated here. And it's asking for the percent difference between these two. Well, the way you would do it, this ends up being the bigger of the two. You know, I'd take absolute values otherwise, but it's the mass of U times G minus the mass of U times G star divided by the mass of U times G, but the mass of U divides out, so we don't care about that. And, oh, we have to multiply by 100 to get a percent. So it ends up being G minus G star divided by G times 100. But G minus G star at the equator ends up being the centripetal acceleration. And so at the equator, it ends up being 100 times the centripetal acceleration divided by G. And so 100 times, well, the centripetal acceleration at the equator was that 0.0339 meters per second squared. Meters per second squared. And I divide by the lowercase g that we get at the equator, 9.8203 meters per second squared. And we'll just keep 3 sig figs on this thing. And you calculate that percent difference, it ends up being about 0.345 meters per second squared. No, meters per second squared divide out. It's just a pure number. Percent is what it is. Okay, so about a little more than 0.3%, not a lot. So that'd be about 3.5 parts per 1,000 actually is what it ends up being. What about in Moses Lake? Well, it ends up being something very similar. In Moses Lake, we'll have our G star equaling 9.805 meters per second squared. And this is what you'd calculate your apparent weight with at Moses Lake. It's actually, yeah, that's actually pretty close to what it is. And then the G is 9.820 meters per second squared. And the percent difference, diff, is going to be 100 times this one minus that one, which divided by that one, it'll be G minus G star divided by G. And G minus G star you can do in your head. It's 0.015 meters per second squared. So 100 times 0.015 meters per second squared divided by 9.820 meters per second squared. And whatever that turns out to be at Moses Lake, percent difference, it's 0.157%. So roughly half or less than half of what it was at the equator. So that's the way that it happens to work out. And then at the North Pole, there is no difference. because at the North Pole, G star is 9.8203, which is what it is at the if the Earth wasn't rotating. And it's because if you're at the North Pole, you're not experiencing any centripetal acceleration because of the rotation of the Earth. By the way, this is that angle between the correct direction to the center of the Earth and the value that you would get at your latitude, because the normal force doesn't quite, well, when you drop something, it drops toward the normal force or opposite the direction of the normal force, but it's not a big difference. And it's about, I think it maxes out at 45 degrees, and it's 0.0017 degrees. So there isn't much difference, but it could be measurable, I guess, if you worked at it enough. So anyway, that's how that one happened to work out. The next problem in the example set has to do with the acceleration due to gravity on Neptune. And acceleration due to gravity at the North Pole of Neptune would be where there's no difference between the acceleration, the true weight, and the apparent weight. By the way, I mentioned here, it would be tough to measure any of these things because the surface of Neptune is just the top of the clouds. But you can imagine, if you've seen episode 5 of the Star Wars movies, this one came out in about, let's see, 1980, I think. I'm not positive about that, but it was weird because in the opening scene, all of a sudden they've got this episode 5, and you start thinking, what? Wait a second, this is the second movie. But at any rate, they had a cloud city in that one, and it was this thing that floated in the clouds. And in a place like that, you experience whatever the acceleration due to gravity is up there, like you would if you were in the basket of a balloon. So that works out. Anyway, it's got a mass of that, a radius of that, 2.5 times 10 to the fourth kilometers, and rotates once around its axis in 16 hours. Interesting thing, the gas giant planets, or also called the Jovian planets, spin faster than the terrestrial planets like Earth. Earth turns on its axis in 24 hours. Jupiter turns on its axis in 10 hours. Saturn's about 12 hours. If you look through a telescope at Saturn, you can see with the help of that telescope, you can see that Saturn is fatter at its equator than it is at the poles. And you can pick up on that. They've got this equatorial broadening because of their rapid spins. However, what's the gravitational force on a 5-kilogram object at the North Pole of Neptune? Well, it's going to be part A there. It's going to be, the gravitational force is going to be mg, and the g is 10.7 seconds, and its mass is 5 kilograms. So 5.0 kilograms times 10.7 meters per second squared. It might surprise you that the acceleration due to gravity there isn't that different than it is on Earth. It's got a whole lot more mass, 2.5 times 10 to the fourth. Whoops, nope, that wasn't the mass. Oh, 1 times 10 to the 26 kilograms. Mass of the Earth is that about 6 times 10 to the 24th. So this would be, let's see, about 16 times as massive as the Earth, but that bigger radius puts you farther away from the center of the planet, and so that ends up basically turning off most of that extra mass for calculating the acceleration due to gravity. Anyway, if you multiply these together, you'd get 50 and then 53.5, which we'll just round to. We only got 2 sig figs, 54 kilogram meters per second. So that's what we get for that one. Well, what about at the equator? Now, at the equator, something there, it'll have the inward force of the true weight there. But then you've got, if you're supporting yourself, you've got a normal force, and the combination of those two forces are what have to give you the centripetal acceleration. So you would take the centripetal force away from that weight. And so for Neptune, if you take and do the 2 pi radians to figure out omega divided by 16 hours times 3,600 seconds per hour to get seconds, it turns out to be about 1.09 times 10 to the minus fourth radians per second. Compare that to omega for the Earth, and I forgot what it was. Let's see, omega for Earth is 7.29 times 10 to the minus 5. This ends up being about, let's see, about 50% greater at Neptune than it is for Earth. So a bit quicker. Anyway, let's see, where are we? Oh, so the centripetal acceleration at the equator is going to be omega squared r. And so it'll be that thing, 1.09 times 10 to the minus fourth radians per second squared times the radius of this gas giant, 2.4 times 10 to the seventh meters. And centripetal acceleration ends up being 0.29 meters per second squared. Okay, compare that to what it is for places on the Earth. And here it's 0.03, let's see, where was it at its greatest value? Oh, actually it's greatest at the equator, of course. 0.03 versus 0.29. So it's about 9 times greater on Neptune than it is at the greatest value on Earth. So it'll have a bigger effect. And G star is going to be the regular acceleration minus that centripetal acceleration. And if you take that away from the 10.7, this is roughly 0.3, you'll get about 10.4 meters per second squared for the effective acceleration due to gravity there. And then the apparent weight, I guess I could put an asterisk by it, will be mg star. So 5.0 kilograms times 10.4 meters per second squared. And again, we can do this in our heads. 5 times 10 is 50. 5 times 0.4 is 2. So you'll get 52. That's kilogram meters per second squared, which is actually 54 newtons up there. We get 52 newtons down here. So that's a noticeable difference. That's about 4% difference on Neptune, and it wasn't ever that big a difference on Earth. So, in fact, what did we have for the percent difference on Earth? I forgot already. At the equator, yeah, 0.345% was the difference on Earth. And on Neptune, it's going to be more like, I don't know, 2/54 times 100. So about 4%, something like that. Okay, well, that was kind of fun. Now, let's do one. This is one of those artificial gravity problems. Suppose we have a giant space station in the shape of a donut, and it has a diameter of 1,225 meters, and that would be the inside floor surface to the inside floor surface. So I'm just going to draw a picture that sort of illustrates this thing. Oops, do it that way. And here's our space station. And it's going to be 1,225 meters from one side to another. And inside this space station, I'm going to draw these too big to be to scale, but are all these little human beings that, I don't know, as this thing is spinning around, they'll be experiencing centripetal acceleration. And the centripetal force, which is the force of this thing against their feet, is what they're going to perceive as weight. And we want this to be one Earth weight. In other words, we want the centripetal acceleration to equal g. And so that'll be v squared over r. It'll be 9.81 meters per second squared. Okay, well, on this one, I'm just going to go ahead and do v is equal to 2 pi r divided by the rotational period. And it's that rotational period thereafter. We want to know how long it has to take to spin this thing. Well, I'm going to need v squared, which is going to be 4 pi squared r squared over t, and then v squared over r is going to be, if I divide this by r, I'll actually get just plain 4 pi squared r over, whoops, it's over t squared. And that thing is supposed to equal 9.81 meters per second squared. Now, if I solve this for t squared, I'll get t squared equals 4 pi squared r over 9.81 meters per second squared. And I'm going to split that 4 into 2 parts. So I'll have 2 pi squared times 2r. And the reason I did that is so I don't have to divide that by 2 in my head. I mean, it'd be 612.5 meters, but I'm just going to leave it that way. And then divide by 9.81 meters per second squared. So this thing is equal to 2 times the radius of it because it's the diameter. All right. Well, if you plug in the numbers, you find out you get t squared is 2.46 times 10 to the third seconds squared. And if you take the square root, you get about 49.6 seconds. So this thing's going to have to turn fairly rapidly, even though it's this giant thing. And that's just the way that it's going to have to be. As long as you don't have any windows looking to the outside, it'd be okay. But like if you were above the surface of the Earth or the moon or something like that, you'd see it completely rotating in your field of view every 50 seconds or so. And it could be nausea-inducing. All right. Well, there's a few problems about apparent weight, and there's an artificial gravity one. But just because we're on a rotating planet, things get a little weird. Now, all of this was assuming that the Earth was a perfect sphere, and I want to change the view here to show you that the Earth is not a perfect sphere. And I think this will work. Let's see. So I'm going to share that. This is the astronomy picture of the day from quite a few years ago. It showed 3 different mountains on Earth. And this is Mount Everest over here on the left side. I don't know if my mouse will show up on this or not, but the left picture is Mount Everest. And it has the highest altitude above sea level on Earth at 8,848 meters. The center picture is Mauna Kea on Hawaii, which is only 4,168 meters. So it's actually less than half as tall above sea level as Mount Everest. But Mauna Kea is the largest mountain on Earth because it starts from sea level. Well, the island of Hawaii formed from a volcano that came up from the bottom of the sea 6,000 meters down. And so Mauna Kea is actually over 10,000 meters tall from its base to the top of it. So it's the largest mountain on Earth. This mountain over here on the right is one that you've probably never heard of, Chimborazo, which is, where is it? I forgot. Actually, it doesn't say, but it's just about on the equator. It's in the Andes, and it is the mountain on Earth where the top of it is closest to the stars. Well, how in the world can that be? Let's see. I'm hoping if I change my view here to this is the Wikipedia page for the Earth, and it's got some stuff here. Physical characteristics here. Mean radius. I better switch my view and make sure we're seeing what I think I am here. New share. Oh, good. Okay. We'll just stick with what we've got here. Let's see. Anyway, it's got this mean radius. It's got an equatorial radius here of 6,378 kilometers or 3,963 miles. It has a polar radius, okay, of basically 3,950 miles. Okay, that means the radius at the equator is 13 miles greater than the radius at the pole. And that makes a difference. It's because the Earth is what's called an oblate spheroid. It's wider at the equator by 26 miles in diameter than it is at the poles. And so if you're on the equator, you're farther away from the center of the Earth, and that greater distance away from the center of the Earth more than offsets the, or is a bigger effect than the rotational stuff. And so anyway, you get different things happening. And then, as if that isn't bad enough, local effects can have a bigger deal. For instance, if you happen to be standing above a large deposit of oil, oil is less dense than water. It floats on top of water, and it's way less dense than rock. And so in a location like that, the acceleration due to gravity can be less because you're not pulled down as hard by the local rocks. And so those effects, those things can have an effect too, as can the altitude that you happen to be at and lots of other things. So latitude, altitude, what the radius of the Earth happens to be where you are, those things all have an effect. And then the rotation of the Earth is tossed in there. So it's all a complicated mess. If you wanted something that was a perfect sphere, you'd go to a neutron star and stand on that, but become a puddle there. So I'm going to stop there, and you can see